So today we are looking at optimization of transportation problem, but using the technique of stepping stone method. We have already looked at how we can carry out optimization of transportation problem using MODI method in our previous discussion. And we looked at the various stages, where the first stage was involving checking the condition of whether the initial basic feasible solution of obtained is non-degenerating, then computing the dual variables, and then after computing the dual variables, we are then obtaining what we are calling the opportunity cost associated with the cells that were not occupied. Then we are doing optimality test using that to obtain opportunity costs. And then we carried out iterative procedures involving drawing loops. Now, the procedure for optimization using stepping stone method is fairly the same. It's only that now we don't go through the process of obtaining the dual variables and then opportunity cost. But in this method, what we shall be computing mostly will be what we shall be calling the improvement index or indices for all cells that will not get a chance to be assigned any units during the determination of initial basic feasible solution. So that then we are going to use this table of improvement index to now carry out a test for optimality. And almost the same I'd say the same approach. Remember, in a MODI method, we were seeking to find a table where the opportunity cost values are all positive. And so even in stepping stone method, we are going to be seeking to get to a scenario where the table of improvement indices gives us all the indices being non-negative. And so a time when we get such, then we shall be able to conclude that the table with the new assignments that has resulted into such indices that are all positive will be said to be optimal. So it will going to be pretty easy compared to the other one. And so I go straight to the steps, and the steps are more or less the same. Like I've said, we are all dealing with problems that have initial basic feasible solutions that are non-degenerating, where the sum of rows and columns less one is actually the number of cells that are allocated or occupied. Then we select the unallocated cells, just like we were doing previously. And this time down, instead of now computing the dual variables, we shall begin straight away the process of finding the whatever I've mentioned, the improvement indices, where it's first of all required to draw closed loops for all those unoccupied cells, then assign alternating positive and minus signs, starting with the starting point. And remember, the starting point of that loop is always the unoccupied cell that has been selected. Then we calculate the improvement indices. We are going to see how to calculate the improvement indices once you have run the loops and assigned those alternating signs. Then we are saying again the test for optimality, that if all the values of improvement indices are positive or zero, then the solution is optimal. Otherwise, we choose the cell with the most negative improvement index. So then choose the minimum value from the cells having negative sign, add this to the cells having positive sign, and subtract. Actually, this statement or this procedure is just the same as what we had in MODI method. And so stepping stone method is more full of loops right from the start to the end and very few computations. And so we shall begin maybe by having an example just to help us demonstrate this. And so I wish that we have an example where we are beginning from the very initial step of determining, first of all, the initial basic feasible solution, before we now get to the second stage of optimizing that solution using the stepping stone method. So suppose we have a transportation table given. It's what you can see here. So suppose you want to determine the initial basic feasible solution and you want to use the least cost cell method. So I want us to do that so that then we can now begin the steps adopted by the steps that we are calling the steps under the stepping stone method. So the least cost cell method, as you recall, we identify first of all the cell with the least cost of transporting a single unit from a unit source to a destination. So in this case, this is going to be the cell. And so we assign that first. So considering the row total and column total, this is going to receive 25. And therefore, I'll have depleted what source 2 can offer. But then destination 2 will still be having a deficit of 5, which will actually be maybe received from a different source. Then from there, again, when I look at the remaining cells, you find that 5 is actually the least. So if I assign between 5 and 35, I'll actually I'll actually meet the desire of destination 2. But then source 3 will still be having 30 more units that will be allocated elsewhere. And so then I compare 8, 7, 6, and 8. So this 6 becomes the next cell to be allocated, and it will just receive 30. So that destination 3 will now remain with 10 more to attain its requirement, but then source 3 will now be depleted. Then from here now you remain with 8 and 7, so that means you'll allocate this cell first with 10, so that now you'll have destination 3 satisfied, but source 1 remain with 10 more, which will actually be assigned to this cell 1, 1, so that we are able to meet the demands of all the 3 destinations and all the sources being able to supply all the units they can offer. So from this, you're able to see that this will be the assignment now. We assign this cell in row 1, and this cell in row 2, and these 2 more cells in row 3. So using those assignments, we can actually obtain that the cost that we are calling the basic initial feasible solution. So we can get the product of that. So when we do the product, so that's giving us 590 as the initial basic feasible solution. I don't know whether we have confirmed, but I know this is an example that we have also used in the previous lesson, so it should be okay. Now, from here, what is now most important for us now for this particular lesson is now to come and see how we can use stepping stone method to see whether we can actually minimize this cost further, or this is actually the minimum amount we can actually spend to transport those goods from their sources to their various destinations. And so that's what we want to do. So the first thing we do is to identify the unallocated cells. We can see now from this table, the cells that have no allocation. This is cell 1, 2. The cell in the first row, second column. This cell has also not received any units. This cell 2, 1. This cell 2, 3 has not received any units. This particular cell 3, 1. So those are about 4 cells that have not received any units during assignment. And so those are the cells we are interested in. And so I've mentioned them, the cell 1 to cell 2, 1, cell 2, 3, cell 3, 1. So we have already begun now looking at the stepping stone method. And so you have each For the cell 1, 2, you may want to investigate it first of all independently. So this is cell, we want to investigate this cell 1, 2, and what you're going to do is we want to calculate the improvement index associated with cell 1, 2. And for us to have that improvement index for cell 1, 2, we draw a closed loop starting from cell 1 to like what you are doing previously. So if I'm starting from here and I want a closed loop, remember the procedure and criteria for drawing a closed loop is the same as the loops associated with the modified distribution method. And so we only draw horizontal lines and vertical lines. You only make turns at a right angle. And you also move towards a cell that has already units allocated to it. So that the loop we are going to draw is only going to have this starting cell as the only cell that is unoccupied. So that like in this case, if you want to draw a closed loop for cell 1, 2, we can only move in that particular direction. Now you can also move downwards. It can either be clockwise or anti-clockwise. Then you can also move this way towards that cell as occupied, because then that way, because it also has some units occupied, and that direction. Huh? So this can be the only closed loop in this case for cell 1, 2. I hope we are in agreement.
Yes.
Thank you. Thank you.
Yes.
Yes, thank you. And then we begin now doing the assignment of those alternating signs I was mentioning, that we are assigning alternating signs, but we are beginning with the first cell, or that unoccupied cell, we are assigning with a positive sign. And so these alternating signs, we are only assigning at the turning points, so that this particular cell is now I'm assigning it negative, and then another turning point, this is positive, and this is negative. Now you realize that whether I assign moving clockwise or anti-clockwise, it will not change the sign of a cell, because even if I was to begin from this cell and then come down here where I'm making another turn, it will still be negative, and the pattern of signs will still remain as it is when you have gone through the clockwise way. And so after assigning, I know in modified distribution method, we are looking at cells with negative signs. But at this stage for stepping stone, we now calculate the improvement index. And the improvement index now is going to be given by, for this particular cell, you now look at, we now use the costs, those costs in each cell. Like the starting cell here, the cost is 9. So the sign assigned to that cell is positive 9. So I'm writing positive 9. Then the next turn here, the cost is 7, and the sign attached to that cell is 7, so is negative. So I write negative 7. Huh? And then the other turn, this cell down here in the corner is positive, and the cost associated with that cell is 6. So it's positive 6. And then this other cell here, the turn is, in this turn, is actually the cost is 5, and the sign attached to it is negative 5. So this is how I calculate the improvement index, by using now those signs I've attached to the cells, then the costs, so that I get now. So the improvement index is in terms of cost as far as stepping stone method is concerned. And so I'm talking of 9 minus 7 plus 6 minus 5 to be the improvement index associated with this cell 1, 2. And this actually gives us what?
3.
This gives us positive 3. Good. So that's how we calculate the improvement index associated with cell 1, 2. Then we move to the next cell that was also not occupied or did not receive any units from the assignment made at the basic initial feasible solution. And we had already mentioned them, but the next one now, maybe in the second row, could be cell 2, 1. And you also draw a loop and get its associated improvement index. So that's why we are now moving to the next cell. The first one has given us an improvement index, which is positive. So cell 2-1. So in this case, cell 2-1 now, we are talking of this particular cell, and we want to draw a closed loop. Again, a closed loop here could be of this kind. I think the same way we had drawn previously. And then you come straight up here. And final here. So you have those. So this is your starting point. So if you are to assign those particular signs, the positive and negative sign alternatively, starting with this as positive, this will be negative, this will be positive, this will be negative, only at the corner points, positive and negative. So that's how the signs will be. So you can also calculate the improvement index associated with now cell 2-1. So you have positive 4 minus 8 plus 7, this plus 7 minus 6 plus 5, sorry, plus 5 and minus 3. So this will be the improvement index, which gives us a value of what? It's minus 14. What's the improvement index in this case?
-1.
-1, huh? Yes. So that's the improvement index for cell 2-1. We move on. The same now, the next cell we are actually performing is cell 2-3. This particular one, and I think here we have to make a closed loop. We could move this way, then downwards, then that way, then back. That's the only closed loop we can have. So if we assign those particular signs, they are going to follow that pattern. And so you can also get the index for this. This will be positive 5 minus 3 plus 5 minus 6. So you are talking of 10 minus 9, that's positive 1. Huh?
Yes.
And then cell 3-1. Cell 3-1. So this is a cell that we want to draw also a closed loop. So a closed loop here could take each format. So this one has to go straight, then again go straight to that far end, then come this way, and finally make a turn to the starting point. So that if I'm assigning positive and negative signs, they'll be arranged in that manner. So that will be a closed loop. And so if I want to calculate the index here, then it will be positive 8 minus 8 plus 7 minus 6. And that will give me 1. Huh? And that will give me 1. And then I think we are done. So we are done with the calculating the improvement indices for all those cells that were unoccupied. And so we need now to make a decision. So we create a table of all those cells that were unoccupied and the improvement indices. So we have already found the first one to be 3, the next one -1, then 1, 1. And so remember, for test of optimality, we said we can only say that we have reached the optimal point if all the values of these improvement indices are actually positive, I use the inequality greater or equal to 0. They could be positive or 0. Now you can see one of them is negative. So that means, what this means is that 590 as a total cost obtained during the initial basic feasible solution will be reduced further. And so that means we need to proceed and see how we can actually do some realignment and the reassignment of the units in that basic initial feasible table so that we are able to get a fairly less amount of cost required to transport those goods from their sources to destination. And so this becomes the cell of interest, the cell 2-1 that has given us an improvement index of -1. So this is the cell that we must make sure that we assign some limits to it so that we check again. So the comment I've said that we can improve the cell with the negative. And so, but then I later emphasize that suppose we had this -1 and this one -3. If we have more than one that are all negatives, you go for the one with the highest negatives. So we could have investigated cell 1 to instead of cell 2, just in case there happens that there's more than one that is negative. So you go for the one with the highest negative. But in this case, cell 2-1 is the only one giving us a negative improvement index. So it's the one that becomes our interest. And how we do now reassignment of units to this cell 2-1 is just the same as what we did in modified distribution method. So remember, this is the loop that we had when we are doing when we are drawing the loop for cell 2-1. This was a starting point, and we had such a kind of loop. And so what we are doing now, we are reassigning units to this particular cell 2-1. And so what happens again, we check cells that have negative solutions or negative assignment of signs. The cells that had negative, this one, and this. So just like in MODI, those are the cells we are looking at. And then we pick the value that is actually smallest assigned to those cells with negative. So when you compare 30, 25, and 30, again, 25 is the smallest. And so this 25 becomes now the units that must now be shipped from their current cell to this new, to this unallocated cell. So we are going to shift this 25 to this particular cell so that this cell 2-1 now can have 25 units. But once we do that, then again, we have to do readjustment in other cells so that now any other cell with a positive sign, we are going to add these 25 units that we have buried. And then any other cell with a negative sign, we are going to minus the same amount so that this has a negative sign, we are going to minus 25 from 30 now to be 5. This one also minus 25 from 30 to 5. Then this one with a positive will now be 10 plus that 25 that we are moving to 2-1. Then this 5 again plus 25. And so when we do that, we are able now to get a transportation table with this kind of format. So that this is now a new readjustment and restructured assignment. So that this cell that was initially unoccupied is now occupied. And we still see the row totals and column totals across balancing, so that doesn't change. And so now in this case, now again, we don't just at this stage conclude that this is actually the table that is going to give us optimal amount of cost required to transport goods from the 3 sources, the 3 destinations. We must again test whether this is actually optimal. And the procedure for that, again, is actually repeating itself. we begin again drawing loops for all the unallocated cells, this new readjustment, and then compute their corresponding improvement indices. And so it's from the table of improvement indices for all the unallocated cells that then we shall be in a position to make a decision whether indeed that this new restructured table is actually the optimal. So that if we shall end up with this being optimal, then we shall just come back and calculate the product of 8 plus 5, or the sum of these products, 8 times 5 plus 7, times 35, 4 times 25, 5 times 7, so on. Then add just the usual way. So before we even do that summation, we now again identify here the cells that are unallocated. There are still 4. And these cells are, we have these 4 cells are allocated. So we begin again drawing loops and calculating the improvement indices for each, as we have done before. So we begin with the first cell 1, 2. And so this is just a comment that we begin again drawing the loops as usual. And so we begin the first cell 1, 2. And so we want to draw a closed loop. So from here, cell 1, 2, if you want a closed loop, if we go on the left, we may not be able to make a closed loop. So we can only make a closed loop if we make such kind of movement. So that now we begin assigning the positive and negative signs. We'll have it that way. And so if I was to calculate the improvement index now for this, it will actually be 9 minus 5 plus 6 and minus 7. And this actually gives us now 3. So 3 is the answer. It's good to confirm.
Yes, mwalimu.
Thank you, thank you. Then we can check cell 2, 2. The next cell is cell 2, 2. This one you also need to draw a closed loop. The closed loop will be this way, coming here, coming this way. Have to move straight where there are units. Then straight where there are units, come here, come here. So that now we are beginning allocating the signs, alternatively positive, negative, positive, negative, positive, negative. So you can be able to get the index. So we begin with 3 minus 5 plus 6 minus 7 plus 8 minus 4. So this gives us 1. 1, huh?
1, yeah.
Thank you.
Yes.
Thank you. So that becomes the improvement index for this cell 2, 2. Then we can have cell 2, 3. Cell 2, 3. I had these tables drawn in advance to make it easy. So cell 2, 3. So you can have, if I want a closed loop, you can have what from here, can move this way, then come this way, then come this way. And that's the only closed loop you can have. So this is positive, negative, positive, negative. So that now, if I want to calculate the index now, improvement index will now be 5 minus 7 plus 8, then minus 4. And this will give us, yes, 2, positive 2. Thank you. And then we have one more cell, 3, 1, which this one, which you want to draw a closed loop. So the closed loop for this will just appear like what we had initially. in that form, so that when assigning now alternating signs, this will be easy for us to calculate the index as 8 minus 6 plus 7 minus 8. And so this will be 1. That will be positive 1. So that from this now, you can now have your table for a new table for the improvement indices and unoccupied cells. So for all the 4 cells, cell 1, 2, 2, 2, and so on. So we found the first one 3, positive 1 for the second, 2, and 1. So you can see all the improvement indices are actually positive. So that means that the table we have just had, the new restructured table, is actually the optimal table and can give us now the optimal cost of transporting now the goods from their sources to destination. And so now we come back to this. So that means that's the final table. We now come back to this table, the new design table, and now get the sum of this product, 8 times 5 plus 7 times 35 plus 4 times 25 plus 5 times 30 plus 6 times 5. We sum those to be able to get now that optimal cost itself. And when we do that, we are able to get a figure of 565. A figure of 565. A point to note, I used the same example like what we use in modified distribution method so that we can actually see the consistency. That whether you are using modified distribution method or stepping stone method, during optimization, you're actually ending up with a similar answer. And even if you check also the method, the VAM method, when we are doing the basic initial feasible solution, if you check, the VAM method also gave us this particular figure. And that's why we are mentioning that VAM is a technique that not only gives us an initial basic feasible solution, but the solution it gives us is also optimal. So you should be checking, because I've used this common example for a reason, so that we see this kind of, we make this observation. So that's what stepping stone method is all about. That is what stepping stone method is all about. We have a question.